Hi everybody, welcome. I have a short screencast here to talk about just a little bit of an intro to Linux and to overlook some of the big picture items here before we delve into the material. So if you would bear with this little bit of a PowerPoint that I'm screencasting here. I'm not really a big fan of PowerPoint. I'm pretty familiar with the death by PowerPoint practice, and I'm not really here to talk you to death. However, these slides give us a little bit of a structure to what I want to talk about and throw a few ideas against you. It'll also give you an idea of what I think is really important about this material. So let's start at first. What is an operating system? Very high level, general stuff. Well, first of all, obviously, before we can have an operating system, you got to have a computer. So this assumes that we already have hardware. We have all of our memory, CPU, I/O devices, storage devices, video, you name it. All the hardware sits there. So before any of that hardware can be effectively utilized, we have to have some kind of software that's going to control all of that. And that's what an operating system really is. So a good beginning working definition of an operating system is simply the first item on this slide. It's software that controls access to hardware resources. Good examples then are CPU, memory, storage device, all other peripherals. In other words, if you're going to have something happen with hardware, it's the operating system that's going to do that for you. Second, and of course also very important, responsibility of an operating system is process management. So we can think of the operating system as the mother of all processes. You can't have a program in execution unless the operating system says you can. So the operating system is really responsible for the creation, management, deletion of every other process on the system. So everything in Unix, Linux, you name it, is going to have a mother of all processes. There's a main process in the operating system that says, okay, I'm going to fire off or fork in Linux, Unix parlance, another process to do something for you. And that really constitutes every other process on the system. Finally, the third major responsibility or feature that you're going to need is you need a user interface, a way for you and I as breathing human beings to talk to the operating system and be able to issue commands and have it carry out our tasks. We're going to see that really you have two main kinds of interfaces here. A command line interface, something where you're typing in text commands from a terminal, which frankly is where we're going to spend the lion's share of our time in this course, looking at under the hood, if you will, of Linux. But there's also a graphical interface, a desktop, the GUI, that of course we're all familiar with. It's really been around since let's say since the mid-1980s with the original Apple Mac. And of course, Windows is another example of that. So that's just a big picture of the things that have to be controlled out there by an operating system. So let's talk a bit about what the architecture of the operating system in Linux is. And at this point, you may hear me interchangeably use terms Linux and Unix. And really, for our discussion, these are the exact same thing. So in Linux and in all other Unixes, we employ a kernel shell architecture, where the kernel is the core component of the operating system. It controls access to everything else, to all the hardware. If you want to get to the processor, you want to get to memory, to the file system, to anything, you go through the kernel. It is the executive layer, if you will, of the operating system. This design has been around since day one. And when I say day one, I'm talking really day one of Unix, which really goes back to about 1969, 1970. There's a whole, frankly to me, interesting history of Unix, but we're going to leave that for another day. This is a very old design and arguably probably older than most of you in this class, and I'm not all that much older than it myself. The point here is that this is really good. It's solid, it's tried and true, it has withstood the test of time, frankly. So let's look a little bit at that. So, in the beginning is hardware, as I said in the beginning of this little chat. And so I'm going to start to build a very simple diagram that's going to look like a series of concentric circles. But it's worth saying that in the beginning, at the very core of all this is the hardware. You have no computer, obviously, if you don't have hardware. So we'll start with that as a notion, and I just enclose hardware in a little circle here. And then we introduce this idea of the kernel. So if you look at the top figure that's in this diagram, you'll see that I have the kernel as one layer, a layer of software that surrounds that hardware, hence the HW in the bullseye of that diagram. This is the executive core level. You know, the metaphor of a kernel as being core as to a seed should be apparent to you by now. Now, more compactly, from here on out, I'm just going to refer to this diagram, looking at the bottom diagram, as simply the kernel. And when anytime you see kernel there in that little circle, I'm really implying the kernel and the fact that it encapsulates all the hardware. You're never going to get to the hardware except through the kernel. That's the important part. So how do we get to the kernel? How do we ask the kernel for things? Well, there is another layer of software written around it, which we're going to casually call the shell. Now, the shell can mean a whole lot of things. But right now, I'm going to start with it being a really simple definition. The shell is simply a series of commands or utilities. We can call those the same thing. These are the commands that we issue that say to the kernel, do something for me. The kernel says, okay, that something's going to, at some level, involve CPU, it's going to involve memory, it's going to involve, you get into hardware, terminal, keyboard, disk files, internet, IP connections, you get the idea. The only way we ever get to those services is through a kernel call. So the kernel totally surrounds and encapsulates this. This is a really smart idea because obviously all of the issues about security and stability and frankly the robustness or the extensibility, the ability to expand an operating system are absolutely predicated upon all of these services being encapsulated in the kernel. The kernel is your one-stop place, if you will, in the software world to get access to the hardware. Other operating systems haven't followed this very rigorously. The most egregious example is Windows. And because of that, that's really probably one of the core reasons for all of the problems that Windows has in terms of its stability, in terms of its ability to support lots of different hardware, in terms of security, crashes, etc. What you're going to find is if you use any kind of a Unix OS, you're going to find a dramatically more stable operating environment. So that's really, I don't want to get too crazy about overemphasizing this, but this is the absolute core, elegant, brilliant piece of really the Linux architecture, and it's been adopted by virtually every OS that's doing anything in the industrial scale, if you will. Even the Microsoft server architecture these days is really embracing a kernel-style design. Okay, so then finally, let's say that there's one more layer around that shell, and that layer is really the user layer. And I've just got a little diagram there with an arrow going back and forth between a terminal, between a computer, but I'm going to call them terminals because that's a really core term in Unix, so we're going to be dealing with that for the rest of this course as well. This is our way of really talking to the OS. The shell out here is the user. I sit at a terminal. There's some utility in the shell that lets me talk to the shell. I talk to the shell and in turn say to the kernel, do stuff for me. Run an application. Let me traverse through the file system. Show me what my files are. Let me copy files. Let me delete files. Let me start up other programs. And in fact, the whole user experience, such as a GUI, is really just a big, sexy shell application. It's just one more application that lives in the shell world that happens to capture your whole session, gives you a graphical desktop, and takes care of the gazillion other issues that are out there. So that, in a nutshell, no pun intended, is really how this whole core of Unix, Linux is organized. And it's really a pretty slick idea. The last thing I want to talk about is just to alert you or to make us aware that there are really two large schools of thought about designs of kernels. And those two terms are a monolithic versus a microkernel. The monolithic model is probably the oldest one. And it's also, I'll tell you right now, the one that is still most used in practice in designing the kernel these days. And I want you just to be aware of that. The kernel is just one big fat program. And in a monolithic kernel, everything is designed together into one big app that sits in memory and kind of pretty much lives there the whole time. All services are provided here. Now, the downside is that it's large. And as a result, it takes up a little more resources. And kernel programmers will tell you that it's a bit tougher to work on, to modify, to extend it, just because of its complexity, it gets to be a bit unwieldy. However, everything being in one place has a lot of advantages, and Linux uses a monolithic kernel. So when anybody ever talks about a Linux kernel, like the 2.6. Whatever version of the kernel, you're going to see that, that is a monolithic kernel. The second school of thought is what's called a microkernel. And in the design mentality of a microkernel, the designers try to offload as much behavior as possible to be outside of the core kernel. So if a job can be done somewhere at the shell level, so to speak, it's pushed there. The end result of that is that you have a smaller kernel in a microkernel. It's somewhat easier to maintain because it's been reduced in its complexity. And frankly, a good mentality for programmers is that the more we can move to small, the better, wherever possible. Now, the flip side of that is that it poses some serious security issues. Maybe I shouldn't say serious, but they're not trivial. Pushing more kernel services out to the shell level allows somebody who has access at the shell level to do things that are potentially a little bit more dangerous. I'm not saying, and I'm not proposing here that that means that microkernel designs are inherently less secure. I'm just saying that from a coding point of view, it takes a little more work. You have to be a little more disciplined and rigorous to sidestep those. The one big example of a microkernel existing in the world right now is really the core of Apple's Mac OS X. The Mach, M-A-C-H, the Mach project, the Mach kernel design effort is a microkernel, and that's what OS X is built on. Now, I know a couple of you out there, at least one of you, is a Mac user. I'm a Mac user. You're watching all of this being done right now on a Mac. And we all know that although it's expensive and there's a few issues with Apple taking control of parts of your world, it's a pretty slick experience. OS X is absolutely bulletproof. It rarely, as an operating system, almost never crashes. I've been using a Mac for 5 years now, and I've had the OS hang up on me literally once. So it's a pretty slick design. Okay, so thanks for your time with this. I just wanted to get a little bit of an overview, give you a feel for how big everything looks, and where some of the big things point in. I'm going to ask you now to go on and start to read the first 2 chapters in our textbook, and there's going to be a couple activities posted. So thanks for your time, and look forward to more. Bye now.